Hello everyone. In this video we will continue with our ordinary differential equations and we will be using symbolic computing. Let's start. So our first example is the second order differential equation here, y double prime. So this is the second derivative of y with respect to t, and then we have y equals to cosine of t. Suppose we are also given the initial conditions at time t equals to 0, y of 0 equals to 1, and the derivative of y at time t equals to 0 is given as 0. So now, in order to use the symbolic computing, we need to define our symbolic variable t, and we use the symbols function, which first we call from the SciPy package. So we can declare this, and t is now a symbolic variable. And then we will define the symbolic function we are representing with y. So this will represent a function y of t. So this is done with this function method. And then we need to define our equation that we want to solve. So our differential equation is going to be defined using the EQ that represents an equation in this symbolic computing package. And then we need to mention that we have the second derivative here. So this is going to be the differentiation of y with respect to t, and we do this twice. And then we have plus y, and then on the right hand side we need to put a comma, and then the second argument here is the right hand side of the differential equation. So this basically defines our problem. Now we can use the dsolve function here that will allow us to solve the equation symbolically, and we will also evaluate the solution if we want to, let's say, create a plot of the solution. So once we use the dsolve with this equation that we already defined, and then we are going to use the initial conditions. So the first initial condition we have is y of t. This subs basically evaluates the solution at t equals to 0 at this point. We define that as equals to 1. And then y prime, again, the initial condition we are given at t equals to 0 is 0. So this part we define the initial conditions for our problem. So once we define the initial conditions as well, then this dsolve will take care of pretty much everything for us, and we can print the symbolic solution that is obtained from this SciPy package. Now we might want to go further and, as we said, create a plot of the solution to understand the behavior of the solution better for a specific domain. In order to do this, we use this lambdify method. Basically, this function translates these SciPy expressions into Python functions. If an expression is evaluated basically over a wide range of values, then e-value f function is not efficient. So here we prefer to use the lambdify function that is going to do this translation for us. And notice that we need to have a grid that is defined for the t values because we want to evaluate numerically. So we have, let's say, the domain from 0 to 10, and we want to have a partition of 100 intervals. So this gives us the t values on our domain where the function will be evaluated numerically, and then basically using these evaluated points of y values, we can create a plot, because now we have our x, I mean this is t, but on an x and y x-axis and y-axis corresponds to t and y respectively. And then we move on to the plotting part. You can see that we input the x values, which is the t values that we have, and then the y values, which are evaluated based on our solution that we obtained. So, and then we can create some title, labels, etc., and then see how does the solution looks like. So if we evaluate this, let me just run and see the plot. That's the name of my file here actually. So we observe that the solution of y double prime plus y equals to cosine t, and as we said, we are restricting our attention to the domain from 0 to 10, but of course you can change this if you like. I mean, for example, you can change this to minus 10 to 10, and if you don't want too many partitions, you can also choose 50 here, just as an example. And our figure, as you see, now changed. Now this is from minus 10 to plus 10, and we have, as you see, less number of points where we evaluate the function. So the function doesn't look as smooth as before because we have reduced the number of partition points here. So actually, if you want a smoother looking curve, you would need to increase this. And you can, depending on the problem, you can change this domain as you wish. So this gave us a nice plot of the solution, and we have seen a useful function here, which is the lambdify. Okay, by using this function, we are easily able to convert the symbolic solution into a numerical function where we can evaluate on our grid points and then create a plot. So let's look at a few more examples before we finish. Another example, so first let me comment out this plot so we don't need to regenerate that. Now let's uncomment this example first, also the solve function. So now let's say we have another problem, second order ordinary differential equation. This is a linear problem. We don't have any nonlinear terms in terms of the derivatives of y and y itself. And how can we define the differential equation for this problem? Well, as we did in the previous example, you just need to use the differentiation operator here. You need to tell that this is with respect to the variable t, and we are differentiating twice. And then we have the plus y. And then put a comma and write down what you have on the right-hand side of the equation. And then this is our symbolic equation that is defined already. And the next step is just to use the dsolve function with your equation as the input, and then just print the solution on the screen. And let's run it. So as you see, the solution is printed on the screen, and the solution here is given like this. C2 and C1 are arbitrary constants here, because remember, we didn't give any initial conditions into this dsolve function, so it produces us the general solution. Okay, if you want to get a special solution, then you need to input the initial values, like in the previous example, we have actually defined the initial values here and then input into the dsolve function. But here, for this second example, we are not given any initial values here, so we can only calculate the general solution for this problem. And one more example. In this problem, we want to solve the third derivative of y minus 2 times this y double prime plus y prime equals to 10. As usual, you just need to define the ODE, the ordinary differential equation, and then use the dsolve function directly. That will produce you the symbolic solution for your problem. Of course, if you want to plot this, then you can use the lambdify function again to evaluate on a specific grid points. Our differential equation, we have the third derivative of y and then minus 2 times the second derivative plus the first derivative equals to 10 on the right hand side. So we call the dsolve function and then print the result. So let's verify what we get. For the last problem, as you see, the solution is given here in terms of the c1 plus 10 times t plus c2 plus c3 times t exponential t. And you can also try to solve this analytically by yourself on a piece of paper and then perhaps compare these results to check your computation as well. And for the previous example, we see that the result is given here for the second order ODE. So as you notice, for the second order ODE, we end up with 2 arbitrary constants as expected. And for a third order problem, here we end up with 3 arbitrary constants, C1, C2, and C3. So we have given a few examples on solving the ordinary differential equations using the symbolic computing package in Python. Thank you for watching.